In this video, I'm going to go over the solution to the second water balance equation problem. And this problem introduces something new, which is a way to look at the water stored in the subsurface. So this is a cross section of the earth with my proverbial tree indicating it's a cross section. And as we go down into the ground, we find that there are two zones of moisture that we encounter. Near the surface, we encounter a zone we call, and I've colored it light blue here. This is called the unsaturated zone. The unsaturated zone is characterized by pores between the solids that contain both water and air. So if I were to look at a detailed view of the material here, I'd have a bunch of sediments here, like sand grains or silt grains or something like that. And in between the spaces of these, there is pore space. Within that pore space, what I find is that there is some water. So in here, I'm going to find some amounts of water. That's sort of the blue stuff here. But there's also some air. And the variable that characterizes the amount or the fraction of water in the unsaturated zone is called the moisture content. We give that the symbol theta here. This is the moisture content. It represents the volume of water, the small volume of water in those pores divided by the total volume of the soil. Now, if we go down farther, eventually we hit a surface we call the water table. We usually give it this symbol upside down triangle. And beneath that surface, all of the pores are saturated with water. There is no air. This is called the saturated zone, and it's shown in that more darker blue color here. So if we were to go look in detail at what's going on down in the saturated zone, we once again have our sediment. And in the pores of that sediment now, though, we find that all of that pore space, all of the pore space now is filled with water. There is no air anymore. So we can characterize the water content as simply the pore space, since all the pore space contains water. So the variable we need to describe the water content of the saturated zone is the porosity, which is given the symbol N. So this is moisture content here. This is moisture content of the soil zone. Oh, by the way, this is called the soil zone. And this is the groundwater zone. And within the groundwater zone, the porosity with symbol N describes the fraction of water in the material. So that would once again equal the volume of the pores, which is equal to the volume of the water divided by the total volume. So using these equations then, if I want to know the volume of water stored in the unsaturated zone, that's V sub W, I'll do that in a different color here, I nearly need to multiply these out. So within the unsaturated zone, the volume of the water can be found by taking the total volume of the soil zone times the moisture content. Beneath the water table, the volume of the water stored beneath the water table can be written at, that's a W, as equal to the total volume of the groundwater zone times the porosity. Now in this problem, what's happened is the water table has changed. So what's happened now is the water table has risen. I'll try to draw it over on the right-hand side of this diagram. So the water table is going to rise, say, to this level here. So this is going to be my new, let's give it a different color to make it clearer. Let's make it purple here. So my new water table is this level here. This is my new water table. And when that happens, notice that this changes the thickness of both the saturated zone and the unsaturated zone. So this change here, I'm going to call that delta H. That's the change in the elevation of the water table. Positive means it's rising, it's raising the water table. So the volume of the saturated zone has increased. and the volume of the soil zone has decreased. So what we're doing is we're converting pores within this little zone right in here that were unsaturated. They had some air in them, and we're completely filling those pores with water, which is increasing the amount of water stored in the subsurface. So within this area here, the change in the volume of water equals the increase in the water stored. Let's just call this volume here. This is going to give us the volume here is the volume of total changed. That's changed. So the volume of water, the total changed volume, that is that region, the volume that has been converted from unsaturated zone to saturated zone. We increase the amount of water we can store in the pores in the saturated zone by multiplying that by the porosity, but we also decrease the amount of water that is being stored in the soil zone because we have a smaller amount of soil zone, right? This is a loss in the volume of the soil zone. At the same time, it's a gain in the volume of the saturated or groundwater zone. So as we transform soil zone to groundwater zone, we gain amount of water stored in the groundwater zone and we lose an amount of water stored in the soil zone. So let's go look at the Excel solution to this now, and we'll talk it through. Now, first of all, this is really similar to the first problem, so I'm actually just sort of modified the spreadsheet. I'm doing this in Excel. A couple of important differences are that everything is now in English units. The areas miles squared, evapotranspiration and precipitation are in inches per year. Stream flow is in cubic feet per second CFS. Delta H here represents the change in the water table, and it's gone up by 2.5 feet. So once again, that is expanding the groundwater zone. We're storing more water in the groundwater zone, but that's contracting the soil zone, so we're storing less water in the soil zone. We want to keep both of those separate. The porosity, that is the fraction of water stored in the groundwater zone, is 0.20 or 20%. The moisture content, which is the fraction of water in the soil zone or the unsaturated zone, is 0.08 or 8%, which kind of makes sense. The difference between the two is air present in the pores of the unsaturated zone. So once again, the way we work our solution, we first need to find a common set of units we're going to use, and in this case I'm going to use cubic feet per year. We're going to use the English units of cubic feet per year. First thing I do then is convert my area in square miles into cubic feet. I'm sorry, square feet, right? Next, I'm going to calculate the change in the volume of the groundwater zone. So remember, this is going to be the negative of this positive change in the volume of the groundwater zone is going to be also the same as the negative change in the volume of the soil zone. And I'm going to calculate that by taking the change in the height of the water table, 2.5 feet. I'm going to multiply that by the area of the watershed, which is in cell B9. So I multiply that 2.5 feet times the area of the watershed, and this 6.7 times 10 to the 8th represents the number of cubic feet that have been changed from soil zone to groundwater zone. The increase in the volume of the groundwater zone and the decrease in the volume of the soil zone. Moving on then, these are sort of similar steps. To calculate the additions of water by precipitation, I take the precipitation rate in feet per year. So I have to obviously convert these inches per year, 52 inches per year, into feet per year, and then multiply by the area of the watershed, and I get 1.17 billion cubic feet per year. The same process is used to convert the evapotranspiration rate in inches per year, convert that to feet per year, then multiply by the area of the watershed to get the evapotranspiration flux in cubic feet per year. So these things, it's a pretty similar process to what we did last time. The stream flow, remember, is given in cubic feet per second, but my standard unit here is going to be cubic feet per year, so I have to convert that from cubic feet per second to cubic feet per year by multiplying by the number of seconds in a year. I do that again. And now these last three terms pertain to storage. I'll give them a slightly different color here so it's clear that these are pertaining to storage, okay? So the first number is the change in the water stored in the groundwater zone due to the water table increasing. And I'm going to get that by multiplying the change in the volume of the subsurface that has increased the increase in the volume of the groundwater zone. That's this number I calculated here in B10. I'm going to multiply that times the porosity N in cell B6, and that is a positive increase in water stored in the groundwater zone. The next thing I'm going to do, though, is calculate the decrease in the amount of water stored in the soil zone, because now we have less soil zone. So I'm going to take the negative of that volume of soil that's been converted from soil to groundwater, and I'm going to multiply that times the moisture content found in cell B8. So as the water table has risen, we've gained 1.35 times 10 to the 8th cubic feet of water in the groundwater zone, and we've lost 5.41 times 10 to the 7th cubic feet of water in the soil zone. That should make sense to you, because as the groundwater zone expands, the soil water zone contracts. So we're able to store less water in the soil, but more water in the groundwater zone. And if I sum the two numbers in cells B14 and B15, I get the net change in the water stored in the subsurface. So that is the sum of those two things, and you can see that it's slightly positive. That is to say, we gain more water in the groundwater zone than we lose in the soil zone. So the net result is that as the water table rises, we actually are storing more water in the subsurface, and that amount of water within this watershed is 8.11 times 10 to the 7th cubic feet. And the rest of the problem is really similar to what we did for the first one. The equation for the water balance equation for the watershed is shown here. We solve it for G. Remember, G is the thing we don't know. So G is equal to the change in storage, which we just laboriously calculated, minus the flux in from precipitation, plus the flux out from evapotranspiration, and plus the flux out from streamflow, all of those terms being in cubic feet per year. And they're all shown in green here. So when I plug in all those values, I end up with a value for G, the groundwater flux, of negative 2.1 times 10 to the 7th cubic feet per year. Now remember, in my first equation, I wrote it out as if G was an input, right? I added it. There's something adding water to the watershed. So if my calculation shows the value of G to be negative, that means that in fact groundwater is flowing out of the watershed. It's an outflow of water. So my conclusion therefore is that I'm estimating that the effective groundwater is that I'm losing about 2.1 times 10 to the 7 cubic feet of water per year from this watershed. And despite that loss of water, the input of water from precipitation is sufficient to actually have caused, in this case, the water table to actually rise by 2.5 feet. That is all part of the numbers that have been used to calculate this outflow of groundwater. So that's how you solve another type of water balance equation in a watershed, this time using the concepts of changes in water stored in the subsurface.